Welcome to another problem session. So, we are doing this MCAT JEE joint prep. So, we've done a whole bunch of sections from mechanics, and now we're on to we did momentum earlier. Okay, so from momentum, normally you will go to energy, but I'm going to jump and talk about a little bit of torque kind of ideas. So we had a momentum, and then we did kinetic energy, and then we're going to talk torque and balance, and then we're going to go back to energy, and then we're going to do rotation. Okay, so let's talk about torque. In this idea of torque, I think there's a lot of confusion when students learn first time. So I would say there are a lot of hand wavy things going on the torque kind of thing, and let's do the hand wavy thing after we do the algebra. Okay. I feel the trouble is you learn the hand wavy thing, and then when it comes to doing the algebra properly, you kind of started to hand wavy there also, and then that's where you get into trouble. Okay, so the algebra part is, so there is some point in space. I'm just going to call it point O, and over here maybe there is some body here, there's an object here, and on that object, at that point of that object, there is a force on that object in that direction. Okay, I just randomly picked it. Okay. So from here to that point, so let's call that point, the point that's applying is P, just to make sure it's a point, and this is another point. And so there will be, from one point of the space to another point, there will be a vector. This vector was a position vector for that point P with respect to O. So if you had a coordinate system, this will be position vector. It doesn't have to be origin, it's just a point. So this is just a vector from O to P. And I forgot to mention that this is a force, this is also a vector. So the cross product of this with that is the torque. So you define the torque. Torque is also a vector with this squiggly thing like this, looks like a T, but this is a tau symbol. Sometimes people use N for that, and sometimes it's also called, here is a torque, and sometimes, especially in the older books, you will say moment of force. And here it is force F about O. So the torque about O. So I like to actually put O down here just to remind myself. And this is, by definition, this thing R cross F. So R cross F, this is a vector, so you have a magnitude rule, and you'll have a direction rule. The magnitude will be, if you draw this plane, these two vectors will make, the area of this plane will be the magnitude of the torque. And if you if you say, okay, how do I figure out that area of that thing? It could be, say, it's a parallelogram. So let's see this R, let's extend that R in this picture. And if this is between, so this, draw the R vector from P and draw the F vector from P from the same point. I know R vector is from O, but I'm going to draw from as if it came from P, the same direction. So this is R redrawn. That angle between this R, this F, I'm going to call this theta. So this angle is the same as this angle from down here. Now you know you can do, area will be area of this rectangle. Now I have rectangle area, so I have to figure out just this distance, and that will be R sine theta. If this is R and this is 90 degrees here, so R sine theta. So this is going to be R F sine theta. This is the magnitude of R, this is positive, and this magnitude of F, that's positive. And so you have a sine theta. So depending on which way this angle is, this angle can be, so, in the sine of theta, this is 0, this 180 degrees. It's all positive here, right? So this whole thing will be positive. Whether it's pointed this way and all the way down here, it looks like a positive, right? So what we're going to do is the angle is that we're going to do is smaller the two angles. Like let's not get too much lost because I'm losing time right now. So R and F and sine theta. And the way we're going to have the sine part will be in the direction. And the way we're going to do the direction is going to be right hand rule. I don't know if you can see right and left over there. So I sweep from R to F, and thumb is going to give me the direction. So that's one way to do the direction. So another direction is, if I were to rotate about, this force was trying to rotate whatever object is going to have this kind of rotation. So if I look from the above, it's going to rotate excuse me, it's going to rotate clockwise about this. So that kind of thing will also, it has positive. So in the same diagram, let's see, we had one more force. So this force was this way, and there was another force this way, exact opposite direction. So, and maybe even do the same place, okay? So you have a force F1, but another force is F2, and that's the point O. So they have same R. So F1 is trying to rotate it this way, and F2 is trying to rotate this way. So this, if we call this plus, then this minus, or vice versa. Okay. So it's the relative sign that matters in the problems. Plus or minus. If it just by itself, then actually this is immaterial. Okay. Just say which way, clockwise or counterclockwise. If there are more than one force and you have to put them together as a add or subtract, it's like this force, this torque tau 1 and this torque tau 2, they will subtract, net effective subtraction. Okay, so that's torque about point. So that can cover. Let's look at torque about an axis. So this is the most natural thing that we see in the interactive classes. So one of the things is, say we have a door, and here's a doorknob, and here's the hinges. So these hinges naturally provide an axis. So if you pull the door, then you're trying to rotate the door this way. If you push on the door, if you push on the door that way, then you're trying to rotate the door that way. So this is going to be about the axis. And the question is, what will be the magnitude? So if this is the axis, well, let's look from the top. And so we look at the force in some plane. Let this be the axis. So if you have a say force over here, let's draw the color, and it's pointed that way, so let's call this force F1. Then we will draw in this plane a 90 degrees to that. So this is called line of force. And so not where the force acting around P, but if you draw from where this plane, which is perpendicular to the axis and contains the force. So this is a plane perpendicular to axis and contains the force. Then you draw a line for this, and then draw 90 degree to that line. This is going to be the so-called closest line to axis. And so this length of this line is called lever arm. So this is also called lever arm for F1. So in this case, the torque of 1, the magnitude of the torque will be a vector, but the magnitude will be, so it's a vector, magnitude will be this lever arm times the magnitude of the force F1 of the force F1. And we say this perp means perpendicular to the line of force. So this whole process defines how you're going to have to find that for each force. The direction again, and the direction is, you can do right-hand rule, or you can do some other rule maybe. So, but you can see that if I was looking from above, this force is trying to rotate it that way, trying to cause this kind of rotation. So look from above, it's going to go like this, and which going to be counterclockwise. So the direction will be, we say sense, so-called sense of rotation. Object doesn't have to rotate, okay? It just what is the sense? So here in this picture, if you look from above, is counterclockwise from above. But let's see, if I instead of looking from there, somebody's looking from here, looking from bottom, it will be clockwise from bottom. So it depends on where you're going to look, from the top or look from the bottom. So you got to tell the That's the problem with this sense of rotation. Okay, so you got to describe all of this. But if you have just one force, it really not very useful information. But basically, if you have more than one force, then which force is going to add up and which force will subtract as far as their torques are concerned, then it matters. So over here, let's draw another picture. So here is so you were doing maybe a pull and then push like that. Okay, again I see my cursor is off, so I'm gonna turn it off and turn the cursor on so you can see where my cursor is more easily. All right, so let's draw perpendicular axis, and so here is the that axis is a hinge. Maybe there's a force over here, and then there's somebody's pushing at this point from the back. So there is a force over here. Let's call it F1. Over here, somebody is pushing from the back. Well, then we got trouble now. This is not in that plane, so we have to draw another plane. Another plane in which the point through which the axis cuts and this line is in this plane. So now we draw the perpendicular from that point where the axis cuts this plane, and that's, so force was acting over here, and so this is the line of force and this is the direction of the force. Here I have to extend, so acting at say P, and this is Q. So here I had to extend it to get the perpendicular to land. Okay, so this is R1 and this is R2. Of course, this is perpendicular and this is perpendicular. But if you think about it, so this is axis, and this guy is trying to do that way, this guy is trying to do that way, and this basically is on the door. These two forces are acting on the door, so this is the torque on the door. So torque 1 is R1 perpendicular F1, and it's got, from looking from the top, it's got the counterclockwise, but tau 2 is R2 perpendicular F2, but it's clockwise. So if you say I'm going to call this a plus, then this will become a minus. The tau net will be R1 perpendicular F1 minus R2 perpendicular F2. But you don't know it's going to be positive or negative. So if I add these guys up, say you got this is going to be Newton and this is meter. Okay, so it's going to be unit of Newton meter. An example, suppose I get a plus 10 Newton meter. Well, because I got a plus, it's going to have this same sense as the plus I chose. Okay, but if I got minus 5 Newton meter, okay, got a negative, which means this guy won in the battle. So it's going to be this guy's. So if it answers like that, then it's going to be that sense in the end. So that's what the whole thing is. So these are torques, and let's see how I'm going to do. Those are, I wanted to make sure that you understand torque. Very clear in the definition of torque. A lot of the people don't get the definition right, and that's half the battle. So I'm going to do this a simple cantilever problem. In the future, we're going to do ladder and other kinds of problems, but today I'm going to do just a cantilever problem. So cantilever is basically a beam or platform. So it has a mass m, and this is the center, okay? And we can support it on, and let's see another support. It has to be beyond the gravity, otherwise it's not going to be stable. Now let's do just this problem. It's done in pretty much every book, but let's do this problem. Is what is the distance that will keep it stable? Okay, so there is a distance a. A gets a certain distance depending on what it is. So this is L over 2. B. So it says, if you let's complicate it a little bit more, okay? Let's put a child sits on and keeps scooting over, and at some point is going to topple over, okay? So if the child goes all the way to C, that's let's call this safest point, okay? And then we're supposed to figure out what is the balancing of the forces. The different forces will be. So examine the equilibrium for this thing, okay? So first thing to do is we identify the forces. So this is the weight. So this weight. This force is just big mg, and let's call this child m. Okay, and L over 2 is this big from here all the way here is L. All right. We can just call this little d rather than write too many L and 2. Just write the d. Okay. And then there will be a normal force here, and then there will be a normal force here on the plank, and the child's weight will act like a normal force. So over there will be a normal force, but that will be equal to, the child doesn't have acceleration. So if you look at just child as a system, you can say this basically is little mg. So let's call this n3. So let's figure out the equations that we will be able to come up, okay? I'm just said my advice to you is to just let the equation speak to you and not just guess all the equations right from the get-go. All right. So one type equation will be, there are no horizontal forces here. So we just look at the axis as y. So sum of all the Fy will be 0. So the balance in this system requires sum of all the forces vector-wise is 0. Okay. This means add all the forces. This means sum. This symbol sigma used to denote I'm going to add up. Second thing is sum of all the torques which have to be added vectorially to 0. So here we only going to deal with torque about this axis and that axis. So this will be axis by axis. So So if both are 0, and this will be about any axis we choose. Okay. I didn't go. Let's go back here and make sure there's one more special case here. So suppose two more special cases here. If I was, this is the door, and if I was pushing the door up, so here is a handle, and pushing the door up, this will this line of force and if you draw perpendicular like that, not the distance between them remains the same, and this force will not, so such a force F3 torque 3 is 0. Another important case is if I had a force I was pushing on the door directly so that this line actually meets the axis, for that torque 4 will be 0. So these are really important cases to remember, that if it's a parallel to the axis, torque will be 0. If it's going and anywhere going to cross the axis, torque will be 0. Okay, and this is very easy to see because the torque the lever arm will be 0 for this. All right. Okay, so about any axis, these are two rules. So let's work out so this is component wise with just y component. So this will give me just one equation: n1 up, w down, n2 up, n3 equal to 0. I'm just calling it n, although we know that it's going to be little mg in this case. Okay, so now I have to pick axis, and it's about any axis, right? So we can pick an axis. Pick an axis this like this. So axis 1. N1 have a 0 torque. N2 is parallel to the axis. Is going to have a what do you think if the axis is like that? All of this will be 0. So the axis 1 is all torques are 0 by themselves. So this is not going to work, right? What we have here is axis, say through this point, but I choose axis, and that's what it's going to rotate. So it's going to rotate about that. So there I do have so this not that can actually going to choose. Let's call this A11. Let's call this axis A12 through the point 1, and torque of N1 will be 0. So axis A12, but torque of, you can see over here, this point and this, so there will be a vertical plane through which this thing is passing, right? So this is the plane that's perpendicular to the axis, and this at that point, so that's the closest distance, and that will be d minus a. So torque of W will be W times d minus a, and it's going to go rotate this way, and that's going to be clockwise. And torque of N2 will be just opposite of how this was. Torque of N2 will be, we need from here all the way here. So we have B minus A into B minus A. and then I have N3, which is same sense as this guy. Torque of N3 is N3 N3C minus A, because the axis is already A here. Now these guys are counterclockwise and counterclockwise. Okay, so these will all add to 0. So I don't care which one is plus, plus, minus. So if this guy is, so let's call this plus, plus, and this is minus. So we can just write down minus W D minus A plus N2 B minus A plus N3 C minus A equal to 0. So this is equation 1 and this is equation 2. So let's look at it. So we have like N2 is unknown. I mean, all these symbols, there will be so many symbols. This may be given. So I'm not trying to figure out a particular unknown in the problem. Just figure out conditions that I can get. And once you know how to condition, some of these conditions may be useful, some may not be useful, some may be easy to calculate. Depending on the question, you can just answer any of these problems, okay? So now we can actually do, how about we can say another axis, try another axis. So another good axis to try will be this. Kills N2 from the problem. If you try this, all torque will be 0, so this axis is no good. 8 to 1, this axis is no good. So you try this axis, 8 to 2, and if this 8 to 2, weight will try to rotate it this way, N1 will try to rotate upward that way, and this will try like this. So N1 and N3 are acting the same way, but the weight is counterbalancing that. So from axis A to 2, from that axis, W times you have B minus D minus N1 B minus A minus N3 C minus C minus B, that equals 0. So that's all you're going to get. You're going to get this equation, and this equation. That's all. They have to give you sufficient number of these symbols in the problem for you to solve for the one answer or two answers. So from this you can get 3, right? 3 equation 3. Everything else you're going to try and say, oh yeah, how about I keep trying different axes? Maybe I'll try this axis. This axis. You can try an infinite number of axes, but you're not going to get new information out of it. Okay. So the reason you try this and this axis, it just kind of simplifies some of the formulas. Like this one gives you just N1, N3. This goes N2 and N3. But N1, N2, and N3 is already included here, how they're going to work out. Okay. So that's it for now. I want to do some other more involved problems using statics, balancing forces and torques, before we come back and do energy, potential energy, and problem having to do with momentum energy in the same problem. Okay, so till then, I'll talk to you later. Bye.